So hello everyone and welcome to this webinar, Alternatives to the P-Value and Power, the Effect on Sample Size Determination, presented by NCRE. So today's webinar, what we're hoping to do is to have a discussion about the current controversy about P-values and of course the associated idea of statistical power, and what could we see in terms of changes to how sample size determination is done at the various stages of clinical trials and in wider research. So hopefully you'll get an idea of both that controversy around p-values and what some of the future methods of interest, if you choose an alternative, may be. Before we get started, my name is Ronan Fitzpatrick. I'm the head of statistics here at Statistical. I'll be presenting today's webinar. I've been the NCRE lead researcher since NCRE Interim 3.0, and I've given guest talks and guest workshops at places like the FDA and at JSM. So hopefully you'll get some interesting tidbits out of today's talk and some interesting theory, as well as some practical guidance on sample size that doesn't involve p-values and power. So in terms of what we covered in today's demonstration, in today's webinar, first we'll be kind of covering the current controversy, basically what is power, what is p-values, why are they being criticized currently, and what are some of the alternatives out there in terms of different approaches in terms of doing analysis and inference for your study, but also there by extension how you would do the planning for such a study if you weren't using a p-value or weren't using hypothesis testing, and how that would affect the sample size determination in particular. And then we'll kind of be focusing on two main alternative approaches. One is sample size for frequentist intervals. Confidence intervals would be the common one there. And then Bayesian sample size, which will focus both on Bayesian intervals, but also a brief mention of the idea of Bayesian testing. And then there'll be some discussion and conclusions at the end. Before we get started, just in case there's a few frequently asked questions, if you want a recording of this webinar, it is being done, so that will be sent out after this webinar is complete, and the slides that I'm using will be sent alongside that recording, so you're getting those momentarily once this webinar is complete. If you have any questions, use the questions tab on the right hand side of the webinar screen, and I'll try to answer a couple of these at the end, but any that I don't answer during the webinar, I will email you afterwards with an appropriate response. So hopefully, if you have questions, keep them going, and if there is any technical issues, make sure to ask those questions as well, just so I know to make changes on our end to deal with those. If you want to know what we'll be working on today, just confidence interval for two means, tolerance interval for one mean, prediction interval for one subject, credible interval for one mean, and posterior error test for two sample z-test. So as mentioned, this webinar is being presented by NCRE, which is sample size software used very widely in the pharmaceutical and biotechnology industries, with 91% of organizations having a license of NCRE who do clinical trials for the FDA, with some of those on this slide here. So obviously the hope here is to give a lot of background, but then to show practically how to do sample size calculations for these alternatives to power, alternatives to p-values in a software such as NCRE. Obviously the general lessons would be extensible to other software that does the same thing as well. So sample size determination, I suppose the first thing I want to do is just give a little bit of background about this. So sample size determination is the process of finding the appropriate sample size for your study, a rather generic term, but basically what we want to do is have a study which has a reasonable chance of success given some assumption about what we think is going to happen in the design. And sample size determination is a very common part of clinical trial design for various reasons, but basically we're trying to balance what you can consider the ethical and practical issues that exist in a clinical trial. First and foremost, of course, is that we want to do a trial or study which is likely to generate valid conclusions. We do not want to have a trial that is very underpowered, because what's going to happen in that case is we massively increase our chance that the result or conclusion we get from our study is completely different from what will actually happen in the population. So Andrew Gelman talks about what are known as type S errors, type M errors, with S errors being sign errors, where the sign of the effect found in your study is the opposite of what will actually exist in the population. Obviously a huge issue there, but also type M errors, magnitude errors, where the magnitude of the effect found in your trial is different from the magnitude of the actual effect in the population. Like, you know, you could have a difference of 0.1 or 1 in your actual design, but the actual effect is 0.1, or maybe it's actually 100 and you've underestimated. Both of those would be pretty problematic. But of course, those need to be considered against the cost constraints that exist, against the ethical issues that exist. So, you know, sample size determination is therefore kind of a Goldilocks problem. We want to have enough people so we can make valid conclusions and make a good study, but we don't want to expose people unnecessarily to a treatment regimen that hasn't been tested yet, and we don't want, you know, to create trials that are so expensive that they become financially and economically unfeasible. And of course, for all these reasons, sample size determination is a fairly standard regulatory requirement from entities such as the FDA for confirmatory trials. But if you look at things like the Nature Publishing Group, their kind of study protocol template that they give, the first thing you'll find under statistical considerations is how did you get your sample size? So in terms of sample size determination, it goes without saying that the most widely used criteria is statistical power. And effectively, the power is the probability that you will detect a true effect of a specified size. But it's important to know that statistical power, or perhaps more accurately, what statistical power, the term has become associated with, is the idea of doing hypothesis testing and, of course, by extension, the p-value. So this is often known as null hypothesis significance testing, NHST, in many places as well. So obviously this is the kind of area where you set a significance level of say 5%, and then if your p-value is less than 0.05 or 5%, you come to the conclusion that you can reject the null hypothesis. This is the most widely used form of inference, and that is reflected in the fact that statistical power, which is about really giving you the chance of rejecting, of basically having a significant p-value, given you should have a significant p-value, i.e. say your difference is not, like you have a meaningful difference. That's basically what power is trying to measure, your probability of getting a success in the sense of a significant p-value. But of course, it's important to note that NHST p-values as a concept are under significant scrutiny in today's literature in terms of the effects that they've had on research in terms of their usage. And so if that's happening, and I'll be talking about that scrutiny in the next slide, but if that's happening, we need to ask what are the alternatives that exist out there for inference, so when we actually do our analysis, but just as importantly, we may also want to think about how are we going to design our study if we're not going to be relying on the p-value, if we're not going to be relying on hypothesis testing, and what alternatives exist and what effect do they have on the sample size determination. Because the point about sample size determination, about valid inference, about cost constraints, etc., don't go away just because you've decided not to use power, if you chose not to use power. So what is the controversy over NHST and p-values? Well, there's been many long-standing criticisms for NHST and p-values, which I won't go in detail here, but basically I think the biggest ones and the ones that people are most worried about are their misinterpretation and their openness to abuse. So the misinterpretation is often related to this idea of the inverse conditional, which is kind of the last point here as well, which is basically that in null hypothesis significance testing and the p-value, we're basically getting a measure of how likely our data is given the hypothesis is true, or perhaps false in the case of power. So what's the problem with that? Well, most people would argue that intuitively when we do statistical testing, what we're actually interested in is, how likely should I got my data? Like not how likely is the data I got given the hypothesis is true. It's like how likely is my theory, my hypothesis, how likely is it true given the data that I got? So that's the inverse conditional. And of course we know that the probability of A given B does not equal the probability of B given A in most practical circumstances. So what that means is that when people try to explain what a 5% significant result significant to 5% level is, they often misinterpret it. They say it's like, oh, that means that the results, there's like a less than 5% chance they're due to random chance, or other types of misinterpretations. I won't go through them all to avoid proliferating them, but basically that's very common. Whereas obviously the p-value has a very strict definition, which is the probability that you would get the data that you did or more extreme, given that the null hypothesis is true. So you've created a fixed universe where the null hypothesis, say that the mean difference is equal to 0, is actually true. And all you're saying here is like, if we were to generate data from that world, how likely is it that we would have got the result that we did? There are other issues around the p-value that, in terms of abuse, that are also very significant. Just we have a lot of ideas about p-hacking, about basically like the p-value. If you just do enough tests, you're likely to get a significant p-value just due to its stochastic nature. So that's obviously a major issue, more of an ethical, practical issue. But obviously, if you have approaches which are more robust against that, that'll be very welcome. And there's a couple of other more minor points like that. The p-value is directly related to the n, which means that if you have low n, your chance of getting a significant p-value is very low, and if you go to a high enough n, eventually you will get a significant p-value for any arbitrarily non-zero difference. That's just going to give all probability points are equally likely under the null hypothesis, and 0 just happens to be the most likely one. But at high n, basically any value is likely to be significant that's not exactly 0. It obviously also ignores the effect size. If you quote a p-value without quoting the effect size, which is more common than we would definitely like, then you're ignoring like the magnitude of the effect, the clinical significance of that effect, and other practical issues. And then there's the general Bayesian argument that prior data, prior beliefs should be implemented in your statistical framework. But I suppose despite all of this, it is still the most widely used statistical framework in practice. But that is changing a little bit. Like I suppose these criticisms, they're going all the way back to basically the 50s when NHST became standardized by combining the approaches of Fisher with Neyman Pearson. Somewhat controversial controversial way at the time itself. I won't go into the history of that, but NHST has a very interesting history in and of itself. But in recent times, there's been obviously a new debate kind of brought back to the fore by the statement by the American Statistical Associations on p-values and hypothesis testing, where they emphasized, what the precise definition is, what is, that good design kind of ameliorates some of the issues we have with p-values, but that also that, the p-value is very kind of intrinsically tied to a certain type of design. Basically, the idea of randomized trials is very tied to p-values in most cases, but also specifically focusing on the weaknesses, including some of the ones that I've given above. And so, the supplementary material, I would recommend reading that. It's very, very good. Lots of very different views on the topic. And if you want to get a more opinionated view on it, I would definitely recommend reading all of that. But basically, I think that's precipitated a renewed interest in the topic. And of course, this year we had some articles and papers in journals like Nature and the American Statistician, which have renewed the calls, which themselves are quite long-standing, of basically abandoning the p-value completely and abandoning hypothesis testing completely. But the big open question, I suppose, is what should replace them. And I suppose I think there's two levels to that. I think one is in kind of general day-to-day research being done in university places and stuff like that, like preclinical research, etc., where I think that's a much more open debate. Whereas I think in the context of confirmatory clinical trials, phase 3 trials, I think it's a little bit more narrow, because I think in the first area, there's obviously a strong belief that the reliance on this kind of machine for generating significant results or having, be able to categorize results, people are very much against that. Whereas I think in the context of clinical trials, there will always be a requirement from a regulatory point of view to pre-specify the success criterion a priori to prevent abuse by motivated actors. And obviously that argument does apply for other research, but I think when you're talking about the approval of drugs and such like that, a pre-specified success criterion is basically required to basically prevent undue influence being placed upon regulatory agencies and forcing them to kind of think about things after the results are collected. So I think there's a little bit of a nuance there, but I think in general research, the p-value has definitely not been fit for purpose. So what I'm talking about here is just two alternatives that have been put forward in terms of doing sample size determination without using power. And there's kind of two schools here, but obviously there's been lots of other proposals here, like stuff like for prediction models. There's been different sample size methods for those. But the two I'm going to talk about here are, one is basing sample size not on power, but rather based on the precision of your estimate. So basically, instead of focusing on will I get a significant result or not, you should focus more of your energy and more of your sample size calculation on how accurate you want your final estimate to be. And obviously that means you're going to be using something like a statistical interval, a confidence interval, a credible interval, a tolerance interval, etc. And what you want to do is make sure that the width of that, given some assumptions about what's going to happen, is no larger than some pre-specified length. And so that's kind of a change in focus there. And there's been several different people putting forward methods in this. Obviously, the sample size method for confidence intervals in general terms are quite widely used and quite well known. But Rothman recently in 2018 and Kelly further back in 2003 both argued that confidence interval sample size could be seen as a superior alternative to power in many cases, particularly in general research, preclinical research. The other one is the idea of using other success criteria if you want to base your sample size on some type of test. And obviously the most likely candidate is a set of Bayesian criteria. So basically this is the idea of using sample size based on a different criterion than the power or p-value, such as a Bayesian criteria like the Bayes factor or the posterior error, or basing it on not just the power, but power alongside other criteria. So you want to not just have your statistical power be sufficient, you want to say that it has other aspects that have to be filled as well, perhaps from a Bayesian framework, perhaps from other types of error types, such as your FDR, your likelihood ratio, etc. And then different people have put forward different, like this is a much wider category than the first one, in the sense that people have lots of different views on what success should mean a priori. But like some foundational papers in the area will be Adcock, who did some stuff regarding credible intervals and that kind of framework. Lindley in 1997, who talked about the choice of sample size, a very interesting paper which took a decision theoretic cost approach to sample size calculations. And there's been a wide array of different methods put forward for Bayesian criteria, ranging from Bayes factors to posterior error tests, etc., etc. And for frequentist alternatives like the FDR, the false discovery rate sample size through that prism as well. So this is a much wider category. In today's, we're going to focus mostly on the Bayesian school perspective, but just to mention, this is much wider. It's a much wider topic than I'll be able to cover today. And I think this other idea of other success criterion in clinical trials specifically is, for me, the big open question that they'll have to be answered. Because as I said, in a regulatory context, pre-specifying what success is before the study occurs is such a central part of good regulation, that if you're not willing to say that a Bayes factor has to be at least 30 or your FDR rate has to be at least this value, 0.05 or some other criterion, then it's unlikely to replace the current strict 2.5% type 1 error rate that is obviously the current requirement for phase 3 confirmatory trials in the vast majority of cases. So I suppose the first alternative is interval estimation. So just on the broadest term, what is a statistical interval? Well, basically a statistical interval is one which contains the probable range for an unknown parameter. That might be a mean, that might be a proportion of the expected population, that might mean a proportion of a future sample, and many other different things. And obviously probable here being kind of used in its kind of most broadest sense, but probability under the frequentist framework of it is the probability under repeated sampling. So we're basically saying if we were to reproduce the procedure for the confidence interval or other type of frequentist interval, we're saying that of those repeated samples, we expect with a certain confidence, a certain percentage of those to contain the unknown parameter. And so using the interval approach emphasizes the estimate value, but also emphasizes its uncertainty. So hopefully interval estimation, if you're going to be using intervals at the end for inference rather than testing, that means that you will be looking not just at whether that specific effect size is significant, but you'll have to think about, well, this is the effect size that I got. what does that mean now in terms of clinical significance, in terms of real world significance? And the hope is therefore decouple that idea of significance without looking at the effect size. The effect sizes should be more central to what we think about when we get a result, rather than just the effect size being just turned into a p-value and then forgotten about. But the uncertainty point is also important, because obviously if you have an estimate which is no longer a point estimate, and I think that's like one of the biggest mistakes being made right now in terms of like getting rid of the p-value, is to then just turn around and talk about just about the estimate value as the thing. That ignores the core part of statistics. The whole reason statistics is a field is that uncertainty is absolutely vital to understanding and making inferences of any kind, whether you're going to be using a p-value or not. So hopefully by using an interval estimation, rather than just talking about estimate values or talking about testing, you combine the importance of the effect size value with the idea of how do we deal with the uncertainty with that estimate, which of course is what testing approach is implicitly doing with the degrees of freedom and the variance, etc. So hopefully some things there. Ironically, when you get to sample size determination, the first part about the actual effect size value actually ends up dropping out, because in many cases, the specific effect size that you're going to get doesn't matter to really calculate the confidence interval. It's really the precision of the interval that you're targeting. So you want to know how wide the interval is, and of course, by implication, what you're really focusing on for sample size purposes is that variance, that uncertainty in the parameter estimate. Now, the parameter estimate does have an effect sometimes depending on the type of test you're doing. Basically, is the location of the estimate and the variance of the estimate, are they independent or not, which is true for, say, means usually, but not for proportions. But the basic point here is that the sample size determination is basically asking you to think about what quality of estimate do I want? How good an estimate do I want, in the sense of having a good amount of certainty about the final value I end up having, and the effect size ends up being de-emphasized for the sample size purposes. But remember, sample size is just a means of getting a good estimate. Obviously, if you get a good estimate, then when you start looking at, well, what estimate I actually get in the final study, that's when the thinking has to happen, because you're not tying the statistical method to the testing process intrinsically anymore. So I suppose it goes without saying that the confidence interval in the frequentist school is by far the most widely used statistical interval. And basically, the kind of layman's definition would be the probability that you will have the true value for a parameter, such as the mean or the mean difference or the odds ratio, under repeated sampling. So that's to say, if I take 1,000 different, if I set my confidence interval process at the start, do that 1,000 times, if my assumptions have been fulfilled around like the distribution, etc., then I would expect that if I have a 95% confidence interval, that 95% of those 1,000 intervals will contain the true parameter. Once again, a kind of counterintuitive interpretation. It makes no statement about how likely an individual CI is to contain the parameter, only how likely a proportion of the set of CIs would be to contain the actual true value, with the assumptions being correct. Once again, you have the inverse conditional idea there. This is given your assumptions are correct. So the sample size determination obviously is targeting the interval width. So that's obviously quite closely tied to the idea of the standard error of the estimate, which is kind of tied to your kind of normal law of large number type theory. And the idea is this gives you the correct width on average is what you're usually targeting. Like if you look at the sample size method in the top right hand corner here, that's basically saying on average the n here it will be, this n will give you the correct width. But it's important to note that the interpretation of average here is a little bit unusual. Like you might think that's like the median, like 50% of the time the width won't be larger than it, but due to distributional assumption around the standard error or around the standard deviation, the variance, which is more related to the chi-squared than the normal distribution, in actuality this is actually like the probability of this width being like the true width not being wider than the specified width is actually a little bit higher than 50%. And there's an adjustment for that we can do called the coverage correction to basically specify what probability we want the length to be, the the length to be higher than our target length. So, if we have a target length of 1, we want, by default, if we just use the kind of normal derivation, it might be like 40% of the time, the length might be slightly higher than our target length, whereas we might want to set that to be like 80% chance that it will be ever higher. I suppose it's important to note that, yes, that probably does sound a bit low, but of course the lengths that you're likely to see higher than the target length, most of those will still be near the target length. They won't be like off into the wilderness, way larger than you expect. I suppose one small note I always like to make when it comes to precision sample size is that if you have location independence with the variance, so basically the estimate for the value does not affect the variance of the value, which is true for say the means case if you're assuming z distribution, then the power and the confidence interval can be related effectively as concepts, and basically you can just think of it as like take the lower limit of your confidence interval. We're assuming that higher effects are better in this case, but basically take the limit that's closest to the null hypothesis value, take the difference between the lower limit and the null hypothesis value, so say between 0 and the lower value, and then basically power for that, and that would actually give you, that actually gives you basically the power. So you can see these kind of standardized effect sizes here of k here. And so that's kind of what you can get there. I suppose like it kind of makes sense to a certain extent. If you think about if the lower limit of a CI was exactly on the null hypothesis value, well, you're basically saying that what's the chances that lower limit will be less than the null hypothesis value? Well, about 50% of the kind of implicit distribution for the lower limit is placed right on the null hypothesis value. So in that case, there's a 50% chance the lower limit will be higher than the null hypothesis value, if that makes sense. But of course, we're not focusing on power today. It's just a small note you may be interested in. So what I'm going to do here is just do a couple of fairly simple confidence interval sample sizes, because I think the assumption here is that most of you are familiar with doing this. And I suppose the major thing that we're doing here is that we're kind of changing the framework in the sense that we have confidence level instead of significance level. The standard deviation would be the same thing if we were doing a one sample t-test, but now instead of power, we're targeting the half width of the confidence interval here. So this is taken from a real paper, just looking at Rosiclit's zone for insulin sensitivity from diabetic medicine. And this is just a simple example that we'll just kind of explore very quickly here. So for anyone who isn't familiar with NCRI, in NCRI, the sample size calculations happen in the top left-hand corner here in this kind of spreadsheet type format. Each column is an individual calculation with white rows being inputs and yellow rows being outputs. That is to say, you can solve for the limit, the distance from mean to limit, the confidence interval width, or the sample size, but you need to input these first. And each row is a required assumption for the calculation. So we need to know the confidence level, we need to know the standard deviation, etc. Also note that on the right hand side you can see there's a little help card here giving you guidance on each of these rows. So if you don't know a standard value, say 0.95 for the confidence level, it gives you that there as well as the acceptable range of values. So let's quickly replicate the answer here of 0.95 or 95%. This is on the proportion scale, obviously, for a two-sided interval with a standard deviation equal to 1.7 and a distance from mean of 1.5. And we see that we get sample size of n of 10 per group. We get a little statement here. We could do some plots as well if we're interested in, but we won't focus on that now. So basically you can see here that sample size calculations for confidence intervals are basically just as simple, if not more simple, than doing a power calculation for t-test. So in terms of barriers to why you would consider this approach over like null hypothesis testing, then there really isn't nothing from a sample size calculation point of view. And of course, software like NCRI will tend to have sample size calculations for confidence intervals for a wide variety of all the common type of parameters you're interested in, ranging from hazard ratios to odds ratios, to log odds ratios, to mean differences, to mean ratios, etc., etc. All of those are basically covered in most standard software such as NCRI. So that's not a major issue here. And so the major emphasis here is we have this distance from the mean to limit of 1.5. that means that we want an estimate with a quality of an upper limit with the limits no further than 1.5 away from that, and that that's how confident we want to be in our final result. As I mentioned though, in this case there is something called a coverage correction, because this is only really guaranteeing that on average the length will be 1.5. So, and as I say, on average doesn't even really line up due to the distributional assumptions of the variance and its relation to the chi-squared, with that being more like that being 50-50. It's more closer, I believe, to around 40%. So if you wanted to guarantee that the probability that the length of the interval you'll get in your final analysis is no larger than your target length, you can use the coverage probability to adjust for that. So let's just, this is the same example for two means, except we now have the coverage probability here. So let's just put in the same values we had previously, just for clarity, because you can see here that all the inputs are the same for this example, except for coverage probability. And so you can see here that when the standard deviation must be estimated, its observed value may be smaller or larger than the true value. The coverage probability is the probability the observed interval will be no longer than the specified value of W here. And so 0.8 is a standard value, and you can kind of think of well, this is almost like the power for the interval. So this is like how likely, this is not just we want the confidence level of 0.95, but we also want to say we don't want the length of our interval at the end to be longer than the target interval with a given probability. And so the probability of the width, the coverage probability, however you want to phrase it, is kind of somewhat equivalent to the power of your interval. So definitely worth something considering when you're doing your sample size calculation. But you will note, of course, that because we're being more strict here, the sample size requirement has, of course, increased from 10 to 14. So something to keep in mind as well. I suppose going back to something just in the slide, the coverage probability derivation is a little more complex. But if you looked at this equation here and you're wondering where this came from, if you thought about a constant interval, the actual equation of confidence interval, where the half width basically equals the z statistic, the standardized z statistic, 1.96 for a 95% two-sided interval, multiplied by the standard deviation divided by the square root of n. Well, basically all that's been done for this equation, which is what we used in the first example, is rearranged so that the half width is on the right-hand side and n is on the left-hand side, and then just, we had to square all of this because obviously the n was the square root of n. And that's how that kind of comes around. And those kind of that kind of, I suppose, more naive estimate is where most standard estimates are. But do keep in mind this idea of coverage probability. But as I mentioned, this is right on average. The chances of having a mean, a limit difference that's 15, highly unlikely. It's more arguing that you're more likely maybe have 1.6s, 1.55s, those kind of values, and maybe you consider those to be too not good enough. You really want 1.5, that's when you get the coverage probability involved. So before we move on, because I think the actual sample size calculations in most of these cases is going to be relatively trivial, I'm just going to do a very simple case for the proportion, just to illustrate one of those minor points that I made, that in this case you'll notice there is no mention of the actual value for the mean difference. So this is a constant interval for the difference of two means, but there's no mean difference anywhere here. And that's because we know that with the t distribution or z distribution assumptions for the two means, there is location independence between the actual estimate and the variance. So we only really need to know the variance. But in the proportions case, we know that the variance and the estimate are not independent. We know that the variance is related to p times 1 minus p if we're talking about a single proportion. So obviously now the value of p or the value of pi is affecting, the value for the proportion is affecting the variance estimate itself, and therefore you need to have the effect size, because it's basically the effect size and the variance calculation in a single parameter. But for this case, what we're looking at here is a 95% constant interval, two-sided interval with an expected proportion of 50%. And in this case, they said a sample size of 24 would give a limit distance of 0.2. And you can see that we get nearly approximately 0.2 for the distance from proportion to limit here for n of 24. One other note I'd make about proportions, and indeed talking about more complicated cases in the means case, is that oftentimes you'll have lots of different options for doing the confidence interval approach. Like you could have the log, like you can use the log version of the proportion. You could look at, for rare events, you might want to have an interval, for example, where you want to just have an interval given a probability of observing a single event. Obviously, that's when dealing with rare events. And obviously, there are other adjustments related to things like the finite population adjustment, very similar to what you'd have in a t-test, etc. And like there's exact versions. There's like in the sample case for proportions, there's the Newscomb-Amscomb, and lots of different versions of intervals. So do note that when you get beyond the means case, continuous case, the range of different options available, even if you're even for the same type of parameter, and even with the same distributional assumptions, can vary quite widely. So this example is pretty simple. I hopefully don't need to go through that too much. And then, like these other examples just kind of show some of the variations. But as I mentioned, there's example like for proportions, you'd have the log odds ratio for both the paired case and the two sample case, and various other options. And we're adding more of those all the time for all of those different situations. Before I finish up with the frequentist intervals, I suppose in many cases you'll probably just find sample size for confidence intervals. That's fine. But there are other frequentist intervals that are used and perhaps are underused that can target other types of parameter, basically things other than a parameter value, other than a mean difference or other type of standardized parameter value. And two of the frequentist intervals you may be familiar with, but maybe haven't used in a while, is the prediction interval and the tolerance interval. So the prediction interval is an interval to contain a future sample subject or parameter with a given probability. So there's lots of different definitions of this depending on this, but it's all focused on the idea that you're going to build an interval on a current set of data, and now you want to predict with a certain confidence how you want to create an interval with a certain confidence that it will contain a value from a future sample. So the classic case, the kind of one that you probably were taught in your intro stats class, is the case where you want to create a prediction interval where it'll have a certain confidence level, a certain probability under repeated sampling to contain a future single observation. So that's to say that I have a set of data of say 100 people. I want to create a prediction interval, and that's basically saying that if I get a single measure from a future person from the same population, I want there to be 95% chance that interval will include that future person. And it's not a trivial thing there, because often confidence intervals and prediction intervals have historically kind of been misused or kind of misinterpreted. I think there's a classic case related to drug testing in sports or doping testing in sports, where a claimant in one jurisdiction successfully appealed their ban on the basis that at that time they had been using confidence intervals to basically measure whether your result was considered unusual or not, and they successfully argued, well, actually, you should be using something like a prediction interval, which obviously it tends to be wider than a confidence interval, and they argued, well, this is what you should have been doing, even within the frequentist framework. When we're not even talking about Bayesian stuff here, just frequentist, and they actually made a success. And these days, that's been changed to basically be using things like prediction intervals and tolerance intervals rather than confidence intervals when you're talking about the kind of range of values that's accepted, if it is based on statistical science, of course. And I suppose for sample size determination purposes, it's important to note that the sample size is not based on the actual width you're going to get for your prediction interval, but is actually related to the limiting interval. So I don't have enough time to cover the limiting intervals in this case, but for a single value, it would basically be equal to the standardized z-statistic for your confidence level, so 1.96 for a two-sided 95% one, times your variance, times your standard deviation. So that would basically be your limiting interval in the case of a single future observation. And then it's basically how much wider will your prediction interval be versus that limiting interval for a given sample size. And then there's tolerance intervals, which is an interval to contain a given proportion of the sampled population with a given probability. So rather than talking about how likely, an interval defined, which will contain the mean or for a percentage time given repeated sampling, this is, I want to have a certain proportion of the sampled population with a given probability. So you have the population coverage. So you want to have 95% of the population within your interval, effectively. And I suppose one like small thing to note there, of course, is that to make this from a frequentist point of view, you have to make you basically have to assume what the underlying population distribution is, exponential, mean, etc. And so it is quite tightly tied to having a fairly confident belief in the underlying distribution. To be fair, that's true of most statistical testing, but I suppose it's particularly true for tolerance intervals. And basically, the sample size determination becomes calculating what's known as the tolerance factor, which for all intents and purposes simply replaces your standardized z-statistic and sample size part, and you multiply that by your standard deviation to get your tolerance interval. It doesn't really have as much of a kind of intuitive or important interpretation standalone, but basically that's where the sample size determination calculations come in. They just calculate this tolerance factor, often known as K, and then you can get your n relatively trivially from that. So what I'm going to do is just take some examples of sample size from the two kind of cases that were covered in the original papers that the sample size methods in inquiry are based on, and just quickly kind of show those off to just illustrate what I was talking about there. I'm not going to go too much into them because they basically work quite similarly to all of your kind of standard sample size calculations. So in the case of the tolerance interval, we had a 95% tolerance interval which is a lower interval, and that's explained why it's here. Like basically, exponential distribution is usually for life distributions, and since longer life is usually better, we're kind of looking for an interval where the lower estimate for the lifetime, say of for an industrial process or indeed perhaps for a survival process, we want the lower limit to be L, but then allow, we're happy for the interval to contain any, we're not really worried about lifetimes that are too long. So then we have a 90% proportion covered, so that's the proportion of the expected distribution, in this case exponential data. We want that 90% of that proposed distribution to be in our future interval. We have an exceedance margin here of 0.05 and an exceedance probability of 0.05, and these basically work, I would say, very similarly to the coverage probability correction we were talking about here, except instead of just having a generic one where it's like we just don't want any values of the length greater than our target length, this is actually specifying some upper limit for the kind of the exceedance that's particularly important to us. So in this case, we don't want, if we want 90% covered on average, but we only want there to be a 5% chance that a 95% is excluded, basically. And so, that's the first example. The other example, as I mentioned, the prediction interval is related to the relative width, and that's a relatively simple calculation. Note that in this context, there are two approaches, and you'll kind of see that the other approach, firstly, let me just do it this way, which is basically saying, what is the expected relative width? As I said, relative to the limiting interval, which is, the definition is given in the home card here, if you're interested. So in this case, the limited width was 1.177. So we want a width that's 1.177 times the limiting interval. We have a future sample size here of 1. So this is the classic prediction interval. We want to have a prediction interval for a single future observation from the same population, and we get a sample size of 11. So in this case, there's obviously a slight issue here where it's made the assumption that not the closest value, but the value that ensures that you have less than the expected relative width. But if we go here and we add 10 here, you'll see that this is the closer value, really. So if you want the closest n, this is really just guaranteeing that the length is less than your target length. And so as I mentioned here, there's another approach here with the upper prediction bound, which is really just the upper bound for our width here, for our relative width, with an exceedance probability. That looks pretty familiar, right? And that's basically saying this is the width we're targeting, and we don't want to exceed that with a given probability. That seems very familiar because it's basically doing the same thing as this coverage probability. And so in both these cases, sample size calculations are relatively simple. There's obviously a little bit of homework required on your part if you want to understand where these concepts or values should come from. But once you've figured that out, doing the calculation itself is relatively trivial in software such as Encry. So with the last 15 minutes or so here, what I want to cover is Bayesian sample size briefly. Note that I've covered Bayesian sample size many times in these webinars before, including in the last webinar, which was kind of talking about using Bayesian sample size methods to complement frequentist sample size, or more accurately complement p-value power-based sample size. So today's emphasis is much more like, well, we're not just talking about improving sample size methods, we're talking about using sample size for Bayesian methods. I suppose the wider context here is that Bayesian analysis is obviously becoming more widely popular, whether in terms of sample size or obviously more likely in general inference, due to one, its ability to integrate prior knowledge. One of the criticisms we had of p-values is that it's hard, it's not impossible, but it is difficult, relatively speaking, to do it properly, to integrate prior knowledge. There is stuff like combining p-values, etc., like that. But also it's more intuitive interpretation. That's more of a opinion than a fact. But the Bayesian inverse conditional, like the Bayesian interpretation is the inverse conditional of the frequentist interpretation. So remember, under the frequentist interpretation, it's the probability of the data given that the hypothesis is true. Whereas the Bayesian interpretation, if you're doing a test, if you have some kind of test that like some hypothesis you're testing, is the probability the hypothesis is true given the data. And some would definitely argue that's more intuitive interpretation of what people are looking for when they do statistical inference. But for sample size determination purposes, there's kind of two main schools of Bayesian sample size. One is, in the first one we're going to focus on today, is sample size for Bayesian methods. So this is basically looking for sample size for specific values of Bayesian parameters, such as Bayes factors, credible intervals. Continual assessment method has like the probability of selecting the right level in a phase 1 MTD trial, and things like utility functions. That's kind of the cost theoretic approach by Lindley that I mentioned earlier. And the one we're not going to focus on too much today, though it does kind of come in a little bit today, is also the improving sample size, frequentist sample size methods using Bayesian basically approaches, Bayesian thinking, concepts like assurance, MBL intervals, and in terms of adaptive design. I did a whole webinar on those a month ago. The recording is available on our website. So if you get in contact at info@statsolves.com, we'll be happy to share the recording of that webinar and the slides from that webinar. But today the focus is on sample size for Bayesian methods. And the easiest way to get into sample size for Bayesian methods, and it kind of fits in nicely what we've just covered there, is, well, instead of kind of what some may consider replicating the mistake of trying to create an inferential standard that's based on testing rather than accuracy or variance, why don't we just do sample size if we want to do Bayesian analysis based on credible interval, which is obviously basically the equivalent of a constant interval via the Bayesian lens. So in intuitive terms, a credible interval actually is stating in layman's terms that a given interval has a certain probability of containing the true containing the true value. Obviously that's within the lens of a percentage of the posterior error being within a given credible interval. And obviously credible intervals are one of the most commonly used Bayesian methods for interval estimation. It is the most commonly used Bayesian method for interval estimation. And the methods by Adcock initially and then extended by Joseph and Bellesley. Basically, you can do these kind of intervals for the means and proportions case based on their work. And there is a bit of a complication that comes in here in terms of what your selection criteria is, which I'll talk about in a moment. And there's also different scenarios in terms of whether you know your value for the precision, which is just the reciprocal of the variance. So basically just think precision and variance are directly related. And also, are you just doing a pure credible interval, or are you thinking about frequentist intervals at the same time? That's the MBL thing, which I'll mention later on, but I did cover in detail in the last webinar. So I suppose the easiest way to discuss like the complications comes from actually doing an example. So this is just a table from the original Joseph and Bellesley paper, and I'm just going to replicate the example 2 here, where they had a prior for the precision, a gamma prior for precision with 2 and 2 for the 2 gamma parameters, a hyperparameter of 10, a length of 0.2, and a 1 minus alpha, basically a coverage error or a coverage probability of 0.95. And so I've actually done this basically for the sake of time. I've done this already so I can focus on the actual interesting part, which is what some of these different options mean. But basically the coverage error here, which is just 1 minus the value given in the table below. This is our coverage error, which is basically the proportion of the time that the interval will not contain the true value. So that's just like, you know, and it's now it's okay to kind of make that kind of simpler or more intuitive interpretation versus the confidence interval case. And once we've done that, we then need to think about the prior parameters. So remember, like, it's a credible interval. Like, and now we're going to ask, well, we have a credible interval. We're going to basically assume it's normally distributed data for the purposes of this. And so we're still going to have something where we expect it to be normally distributed. It'll kind of look a lot like a constant interval. But we do now get to integrate prior information into our credible interval. So basically, we need to know what the variance is to get our interval. And so all we're going to do now is, well, like, how much do we know about our prior estimate for the variance? So we can apply a prior to that. And if we don't know anything about that, we might use some of the kind of more standard kind of uninformative priors. But I think for the case of a variance, usually we have some decent idea of the estimate here, and there's obviously various ways you could get the prior for this value. The maximum, you know, today's posteriors, tomorrow's prior comes to mind. But regardless of where you get the prior from, we're assuming here that it's characterized as a gamma distribution for the precision, which, as mentioned here, is the reciprocal of the variance. And this comes down to the fact that the inverse gamma is often used for the variance. But, you know, the gamma distribution is perhaps more intuitive and more well known, and is kind of a standard way of parameterizing in the Bayesian school regardless. And so in this case, you can see that in the gamma distribution, basically lower values of the gamma parameters usually imply that your prior is less informative. So assuming that the ratio of these two parameters is the same, the lower these are, the less informative we're basically saying we believe the prior to be. So in this case, we have a fairly weak prior for the variance. So we're saying that the strength of the evidence that we base this prior on wasn't that strong. Let's keep it weak. And obviously, when we get real data, we'll be updating that to create our much better, our posterior distribution, which will obviously still be quite strong, but will be more influenced by the real data than the prior initially through this. So that's kind of the first thing here. And I think, you know, it's important to note that, you know, if you keep the ratio of these two the same, you can show very trivially that, you know, the prior mean for the gamma is equal to the ratio of these two. So if the ratio is kept constant, that actually means that your estimate for the precision, and by extension the variance and standard deviation, will be kept constant. So if I do that, but I just keep increasing it, so let's say I put these to 200 and 200, this is actually saying, you know, I have a really strong prior now, but that the estimate of the precision is still the same. It's still expected to be 1 because it's, you know, these two divided, you know, the same thing divided by 7 is obviously equal to 1. And of course, in that simple case, you can also easily derive that if the precision equals 1, the variance equals 1, since the reciprocal of 1 is 1, and if the variance is 1, the standard deviation also equals 1. And I'll return to that, that in a second. But in this case, we assumed a relatively weak prior. And obviously, you could see that as the prior got stronger there, the sample size went down a lot. Very unsurprising, of course, because then if we have this prior data, and obviously we're going to be using that properly in the Bayesian framework, we're integrating prior data, using it as it actually, using it as it should be appropriately based on how strong our belief in the prior is. Then obviously if we have a strong prior, and of course we're assuming this is true, we're assuming for the purposes of planning purposes that we got a good estimate of the prior for planning purposes, then the sample size ends up being greatly reduced. The posterior interval length is the same as the confidence interval length, except just note this is obviously the total length, not the half length. And then the hyperparameter n0 is really just what you can think of as your prior sample size. So if we are taking this prior parameter values from a study of size 10, this is an adjustment factor for that. And in real terms, what this often just comes down to is that if whatever you got for the hyperparameter equal to 0, basically where you just got this prior from no previous data, then you just take that away. So you can see there's like a difference of 10 if I set this to 10, etc. Doesn't match exactly in all cases, but that's a good rule of thumb. And so you can see that the parameters required, regardless of your criteria, are exactly the same. And we have a subset here of 0.05 and so on and so forth. So the main difference these things is like what do they allow to be only correct on average. The ACC, the average coverage correction, says we want the coverage, or basically the probability, the coverage error, or probability of containing the true interval, to be only on correct average, while the length will always be 0.2. Is exactly 0.2. The length to be on average correct, but the coverage error has to be exactly right, which is probably, this actually maps on closer to what we think of in terms of confidence interval calculations, but ironically ends up being different, much different in interpretation in extremis to the confidence interval, which we'll see in a moment. And the WOC, which is basically an extension of ALC, but has subset here. And the definition of this is basically very similar to the coverage correction we saw earlier. We just want a 5% chance that the length will be exceeded in our actual final interval. We only want a 5% chance of that. That's what this subset is doing here. And as I mentioned, if we had a very strong prior, you might intuitively think, well, that actually ends up being pretty similar to the idea of a frequentist interval, right? And this kind of comes back to that point maybe you might have heard that confidence intervals and credible intervals don't end up being that different overall. And that actually, you can actually show that to a certain extent, because if I set a 95% confidence interval, which is equivalent to 5% coverage error we saw previously, standard deviation equal to 1, which we note that for the case where the two gamma parameters are the same, the precision equals 1, variance equals 1, standard deviation equals 1, and we set our half distance is 0.1, which is half 0.2, we get a sample size of 385. And if I take the ACC criterion, and let's make this a really informative prior, let's say it's 2000, 2000, very informative prior, very low variance for our prior effectively, we'll see the sample size ends up becoming the same thing as we got for this one, except for the hyperparameter 0, because obviously the confidence interval doesn't take into account that you have prior data. So without any prior data, those become the same thing. And even though in the confidence interval case, we're assuming the error is fixed and the length is variable, it's actually in the Bayesian case where the error is variable and the length is fixed that you end up getting them coming to the same value. And that kind of reflects the fact that it's the inverse conditional problem, like you're kind of focusing on two different things almost, but somehow they end up looking the same if we allow these two things to be, like we're looking at different things being right on average, but yet they end up being roughly the same interpretation. And that kind of comes back to that point that people have mentioned about confidence intervals and credible intervals being quite similar. As I mentioned, MBL intervals are very similar, except that we want to not just have our credible interval be of a certain length, but we also want our confidence interval with the same assumptions about the variance to be of the right length. But I covered those in the webinar last month, so I'm not going to cover it here today. But basically, the principles and inputs are very similar. So if you've done if you can do a sample size calculation for credible intervals, you can do the same for the MBL, the mixed Bayesian likelihood approach. I'm going to very briefly mention the posterior error approach because I did cover it in last term's month, just because the posterior error approach is probably somewhere halfway between being a method for improving frequentist statistics and being a full-on alternative criteria itself, because this posterior approach is allowing you to target the posterior error, but the posterior error is based on allowing success to be defined by the p-value itself. And in fact, if you think about the Bayes factor, and one of the most commonly and well popularized ways of calculating a Bayes factor is a derivation of the Bayes factor based on the p-value. And I think this posterior error approach ends up being very similar indeed. And so I covered this example in the last webinar, so if you want it in more detail, You can see it there. But basically, if we have these inputs here, and just note that these are the inverse, like alpha here corresponds to beta and vice versa. It's a bit unusual. And we have a 50% chance against the null hypothesis. So we are integrating the prior belief against the null hypothesis. We enter 2.6 for our difference in means. We have 10.6 standard deviations per group. We have a sample size ratio of 1. We get 254, which is not too far in this case away from the 524 total. In that case, difference rate 50. But this obviously would change if our this is kind of 50-50 against the null hypothesis is kind of similar, a little bit similar to the frequentist case, I suppose. But if we change these, this prior probability belief against it, things get very different. And you can see that we're automatically getting, for these Bayesian criteria, the frequentist criteria that we're looking for. So a significance level of 0.05, power of 25%. If you want to play around with that more, I would definitely recommend using the posterior error calculator option from the assistance menu, because in this case you can actually go either way. So I can, for a given significance level and power and probability against the value, let's say 0.75, I can get back these posterior errors. Just remembering that this alpha really is closer to this value here. So this is like 76% Bayesian power, and then this is like 0.018 significance level, Bayesian significance level. But I think important to note that the Bayes factor, which is obviously one of the criteria being put forward as an alternative to p-values, there's a very well publicized derivation of the Bayes factor based on the p-value assumption. And I think the idea of the posterior error here, as defined by Lee and Zelen, is very, very similar. So discussion and conclusions. Sample size determination, very vital for study design, with power being the most common criteria, but as I said, intrinsically tied to the NHST p-values controversy. And therefore, if we're going to have alternatives to the NHST p-values, we need to have methods that, sample size determination methods, for those alternatives, much preferably. So if we're going to use frequentist intervals more commonly as our kind of final thing that we're targeting rather than the p-value, then sample size methods are well developed, not just for confidence intervals, but also for the other maybe less well known, but still very interesting intervals of the tolerance and prediction intervals. And I think it is important to note that they do exist and to just not just use confidence interval by default when you're really looking for something else. Credible intervals have that same advantages of, say, relying on an interval framework rather than a testing framework, but have that more intuitive interpretation from the Bayesian framework of, there's a 95% chance that a given credible interval contains a true value. It's still a bit of a simplification, but it's a more accurate simplification, because the confidence interval one is one where 95% of all confidence intervals will contain the true value. Doesn't make any statement about how likely a given confidence interval is to contain the true value. And the posterior error approach is an example, perhaps, an early example of a kind of different success criteria that you might want to consider alongside or in addition to power in terms of doing your sample size calculation. So not just looking for your kind of standard frequentist errors, but also at your Bayesian errors. And things like the Bayes factors and such and so forth will probably lean into that same idea going forward. So that completes the webinar. I just want to thank you all for attending, and I'll be looking at the questions here at the moment. But just in terms of some final bits and bobs, our summer update happened in May this year, so that should be downloadable right now automatically. And basically we added a series of new features, 29 new classic tables, that's fixed term non-adaptive tables in hierarchical modeling and interval estimation, 5 new assurance tables and posterior error related tables, the Lee and Zelen approach, and 7 new adaptive tables related to sample size re-estimation and conditional power. In particular, unblinded sample size re-estimation for survival data is probably the big thing that was added in that update. And you can get the details at www.statsolves.com/what's-new. And just to mention that if you don't have a license for Inquiry, or you don't have a license for the Bayesian or adaptive features, you can have a free trial of those by simply filling in the form at statsols.com/trial. There's no download installation required, so basically you'll be able to use a version of Encre within your browser for a trial period. All we need is just basically your basic details and your email address, so that we can send you on the relevant process for getting into the trial. So if you want to try either Encre in total, if you don't have Encre, or any of the kind of more complex features, that is an opportunity to do so. So any further ado, if you have any questions after today in the webinar, just email me at info@statsols.com. I suppose without further ado, I just want to thank you so much for listening. I'm just going to take a couple of questions here at the end. I'm going to take a moment just to read them and answer a few on air. But otherwise, if you're interested, the references will be in the slides at the end here for all of the examples and other things referenced. And I'll be back in a moment just to answer a few questions. Okay, just a kind of like a general question of like how likely do I think personally, I suppose is what they're asking, like how likely is that like power and p-values are going to be phased out in the near future? Basically, it's a bit longer than that, but that's the basic gist. I suppose personally, as I said, in like Encre, like we're mostly focused on clinical trials, mostly focused on the pharmaceutical biotechnology places. I think the 2.5% type 1 error makes more sense in the clinical trial context for, as I said, one practical reason, which is as a regulatory agency, if you basically say, well, they will get our result or get our inferential statistic and then decide what success means, there's obviously a lot more room there for kind of negotiation, a lot more room there for difficulties, because in many cases the regulatory agencies, they're looking at all these different studies at the same time, whereas each trial is very motivated to have a success, and therefore regularly having a single success criterion means that you have a regularized approach. There's no idea of it being biased. There's no idea of them favoring one person over another. It kind of removes that kind of controversy. It makes their job just easier, even if that means that they might miss a few more results than if they went to a more open-minded approach, like using the interval, like the estimate with its interval, with its interval and stuff like that. I think one other thing is I would note that I talked a lot about the inverse conditional and the more intuitive interpretation. I think from the perspective of a regulatory agency, the less intuitive interpretation of the frequentist school does kind of philosophically make sense. Like, I would argue it's kind of like a devil's advocacy type of argument, where you're, as a regulatory agency, going to assume that the null hypothesis, basically that the drug is ineffective, is usually null hypothesis, is true. So we're assuming that's true. Now tell me how likely it is that what you got in your study would have happened given the devil's advocate's argument that you're wrong is actually true. So I think philosophically, it probably makes more sense in that context. Whereas obviously in day-to-day research happening in universities, happening in companies, happening in preclinical research, that interpretation isn't really as required. That's people kind of doing their own results, trying to get evidence for their hypothesis, which is kind of often ill-defined or not well-defined already. Having a more general kind of more approach, which kind of puts central to it, let's get our results and interpret them then and think about them then and then kind of make conclusions about what we're going to do next based on that, is perhaps makes more sense in that context. And the Bayesian idea of it's the probability of the hypothesis given the data is maybe more the kind of evidence that they're thinking of. That's the evidence kind of level they're thinking of. And there was just one small question about the posterior error approach. I think probably because I skipped over it a little bit too quickly. As I mentioned, I did this in the previous webinar, so I won't cover there, but it's just like where the prior probability parameter comes from. And I suppose just that kind of similar to all prior parameters, it kind of has to come from, intuition, expert elicitation, previous data. That's basically just you going within a frequentist framework, you kind of going, okay, how much do I believe the null hypothesis is true or not a priori? Because obviously one of the big issues, or one of the kind of jokes that you often get about frequentist analysis is like how it would deal with testing that the sun is going to rise in the morning, situations like that where obviously there's such a very large prior probability at play. Why aren't you taking care of that? Why aren't you including that? Which Bayesians would obviously argue. And this is just an opportunity to do that, even if this is, at the end of the day, you're going to base your final result on a p-value. Why don't you just include this kind of thinking, these kind of errors in your thinking at the same time? And like I said, the Bayes factor, or one derivation of the Bayes factor based on the p-value, basically makes a very similar argument with basically the same parameter used to kind of get from the p-value to the Bayes factor, this probability against the null. Okay, there's a couple of other minor questions, mostly related to kind of practical things like the slides, etc., and a couple of other smaller ones. So I'll get back to you by email, but just want to finally thank everyone again for attending. I hope you learned some interesting ideas here, and once again, just thank you so much, and I look forward to having you at the next webinar. Thank you a lot, and goodbye.